All right, good morning, everybody. And thank you for joining us today for this Hermes webinar. We have prepared quite an interesting, ideas and topics to discuss today. This is the agenda of the webinar. We're gonna have a short message from the leadership of this project. We're gonna introduce a little bit the Hermes project itself. And then we're gonna have, some big announcements for our group. We released the beta version of the software this month, and we're gonna go over some demos and some, experiences like configuring, deploying, and running some workloads on top of Hermes. At the end, we're gonna close with some frequently asked questions we have received from early testers and users. And with that, I'll give the floor to Professor Sun, the principal investigator of this project.
Hello, everybody. I don't know everybody can see my camera yet. My name is Xianhe Sun. I'm the PI of this project. Next slide. So I want to very quick give a overview of this project. The first, what the project is. What is Hermes systems? The Hermes systems is a multi-tiered I/O buffering systems for HPC. And of course, later in this session, in the next rest of this 1 hour, you will learn more about the technical part. Well, I want to emphasize here is this is a NSF supported project, CSSI framework. Start this our proposal Sunday the 18. You can see the number funded in 19. So currently the end of the third year. So we have just released this the beta version of this project. So that this year is the first year we have our annual meeting for this project. So who is Huawei? Who are the developers? Mostly is from Illinois Tech. Illinois Tech, this is Anthony, you have seen, so the technical lead for this project. And we also have our really equal partner, SDF group. They are more from this development industrial part to support this, to develop this systems. And also we have other partners to provide applications, to provide facilities, to some tool list here and some are not listed there. We have other partners to join us for the development. So what is the motivation? The motivation is in highlighted, of course, I/O is very important problem for the performance, for high performance computing and for large scale big data applications in general. And also we have this new technology come out, right? Memory, storage, the new device, it's available. The hardware is available. The question is how to use that. And in fact, the HPC industry or community already built this something called burst buffer systems. So handle to use as a buffer for HPC systems. But it doesn't work very well. The reason is currently the burst buffer system have to ask user to do a lot, which become very difficult to be adopted in the practice. The second is, the burst buffer is currently work alone as a buffer systems. We haven't really integrated into the whole hierarchy of the I/O stack or even the memory systems. So there's a limitation for them. Also, the burst buffer design and the same thing as our Hermes design is based on this 80-20 rules. It's basically you get 20% of your application, contribute to the 80% of this delay. And also, only 20% of times they have I/O problems. They get 80% of this contribution of this bad performance. So then we get our solutions. Our solutions fully utilize the memory hierarchy as the left picture you show. And we also fully parallel as the right picture you have seen. Next slide. Okay, then in fact, what is the advantage of Hermes? Hermes is effective. It's fully parallel. So all these tiers, that means all these I/O device, and no matter they are in different layer of your memory hierarchy or in the same layer of your memory hierarchy, the tiers will mean the hardware they have a different performance. All of the tiers can work together concurrently or in pipeline and work together to get the data for you, or either read or write. So this is fully parallel, right? When you get this fully parallel, you get this complexity. How do you handle that? In fact, the user we cannot depend on user to handle that. So you need system optimization, system management. That is the complexity of these Hermes systems. And even the system is very complicated, but we want it easy to use. So this is a part, the Hermes is a part of the HDF systems. So if you use HDF systems, you can use this Hermes automatically. So everything is automatic. So this user doesn't need to do anything to change the code or setting the environment. You do not need to do that. The system will do that. And also, we support the heterogeneous environment, support different applications. As long as you use HDF5, you will benefit from Hermes. And very smart. The Hermes, how that optimize is not only provide system service, they also carry the user information from HDF, go to all the levels to do the optimization. So then you get, with this system is tested, we in fact get in the last 3 years to get a series of papers or technical report to test on different applications, to test our different service. And we not only development that, we also have technical foundations to support our development. And the system are available. That's why we hold this meeting. The system are available now. The beta versions are available for developers or for application nodes to use. And this left corners or right corners, the picture show you the layers of this design, or this architect design for the Hermes systems. I think that is my 4 minutes for this nutshell introduction of Hermes.
Thank you, Professor Sam.
Next, I will turn to NSF Program Director.
Yeah.
Thank you.
Thank you, Professor Sam.
Now it's back to you.
Yeah. So Dr. Jay Park is among us today, and yeah, the floor is yours, Dr. Park.
Hello. Thank you for invitation. Hi, I'm a program director managing CSSI projects, including the Hermes. First, I would like to appreciate the lead PI, Dr. Sun, and other collaborators for their efforts to develop HDF libraries for the memory and hierarchical storage system over HPC. This project is actually one of exemplary CSSI projects supporting HPC communities. I'm happy to see the progress and outcomes in future. I hope that the project can continue to work and sustain the HPC communities too. And I wish to stay a whole session, but I have another meeting, so hopefully I can actually have more talk later. But again, I really appreciate the whole team and collaborators in the project. By the way, we have another program director here, Dr. Sussman.
Hi, Dr. Sussman.
I didn't think you were going to introduce me, Jay. That was unexpected. But I'm here to listen to and hear about the project.
Thank you for joining us. Thank you. And for anybody.
Thank you. Yeah, thank you, Jay. Thank you, Alan.
And for anybody that who's not available for the entire session, we will recording this and we will make available the recording on YouTube and other digital properties. Thank you for that. So let me quickly provide a project overview. Some of the things Professor San mentioned. So traditionally, memory systems and storage demonstrate widely different performance, right? There's a huge performance gap in terms of access latencies, bandwidth, and data representation even. So modern system designs at the same time incorporate multiple tiers of storage in organized in a hierarchical fashion, right? You have compute node local fast flash devices or persistent memory devices. You have best buffer installations. You have a lot of different tiers between your compute and your storage, right? So the whole goal of that is to mask the IO gap between memory and storage. So you have best buffers and you have local flash storage, you have far memory like crosspoint technologies. The thing with that though, this environment is that each system is independently designed, deployed, and managed, running different software stacks like data warp and IME are different examples of best buffers, and usually local flash storage is managed by a deployment of ext4 or XFS, and then you go with specialized PMFSs and Novas of the world. All of this makes it very complicated for the end user to just take advantage of all of that and manage this complexity. So for that, ideally, the presence of multiple tiers of storage should be transparent to the user, right? And without having to sacrifice IO performance. Our proposed solution here is the Hermes distributed IO buffering platform. It enables and manages and supervises IO operations in the deep storage and memory hierarchy. It offers a selective and dynamic layer data placement strategies. It's modular, extensible, and it's performance oriented. Finally, we aim to support a wide variety of applications. Our primary target audience is scientific computing, but it's not limited. Our technologies are not limited to scientific computing, but it can go to distributed computing and any large-scale applications. To increase the ease of use and programmability of Hermes, we also, one of the goals we had in this project was to impose zero or very minimal code changes for the application. For that goal, we developed a collection of adapters within the adapter layer of Hermes. We have a collection of interceptors for popular I/O interfaces such as standard I/O and POSIX and MPI I/O. And of course, we work very closely with the HDF5 ecosystem. We're supporting direct HDF5 workloads on top of Hermes using a virtual file driver. And coming soon, there's going to be a virtual, like a Vault plugin. So before I give the floor to our engineer, Chris Hogan, to give us some demos, I want to make sure that everybody's aware that the system is available on GitHub. And we really welcome and invite early users and adapters and testers to give us feedback. It's a project in the beginning. It's the beta version of it. We know things might not work perfectly at this point. We welcome that. We welcome if you raise bugs or you have requests for certain features to be added. And the way to do that is through GitHub. You can raise an issue and our engineering team will be following up on that. We also have set up a forum and there's a lot of digital properties online, the website itself. So keep in mind, this is still under heavy development. New features are coming up. We plan to release a lot of these features in the upcoming year. And with that, I will switch to Chris.
Okay, I will request the screen here. Okay. So first, I'm going to say a few words about the beta release, what we have, where you can find it, where to read about it, where to find out more information. And then I'll jump to some demos of deploying and configuring Hermes, and then finally running Hermes with IOR, which is an IO workload generator. So as Anthony said, for this beta release, we really are looking for feedback. We've tested several IO workloads, and every workload we try, we find new things. We learn a lot about how Hermes should be. So yeah, if anyone is interested, give it a try. It doesn't require code changes, and we try to make it as easy to install and deploy as possible. And if you run into problems, just open an issue in GitHub and check back in a couple months, because we are planning on a monthly release schedule for the next year as we work towards our 1.0 release.
You can make that full screen. Who is to control this slide?
Yeah, I'm actually going to change to a different window right now.
Oh,
so
okay.
I'll be jumping
Okay.
around a lot.
Okay.
So yeah, I'll jump to our wiki right now, which is our main source of documentation. The Hermes repository is under the HDF group organization on GitHub. And you can find the wiki here at the top. There's a lot of information here. A lot of this is living, breathing design documents. But for people interested in the beta, this getting started guide is the best place to go. It'll tell you how to build Hermes, talk about resources and deploying resources, using adapters. And then there's a tutorial that demonstrates a checkpoint restart workload using IOR. So that's the best place to start. And then, like I said, a lot of this is under heavy development, but you definitely want to look at the Hermes configuration page, because when using Hermes with an adapter, which is the intercepting layer that requires no code changes, all your control comes from the configuration file. So you really need to understand this. And not only is it, cluster specific or system specific, but it's also workload specific. It allows you to tune your tune Hermes to your specific workload. So I won't go into this too deeply right now, but it's there to read about if anyone's interested in trying it out. Next, we have some Doxygen documentation for the Hermes API. This beta release is more focused toward the adapters, but keep in mind there is a full API for full control for new application development available for Hermes, and this is the documentation for that. This will also be changing a lot over the next year, so if something's missing, check back in a month. That's everything I wanted to show for the release information, so I'm going to jump into my demo. And rather than doing a live demo, I just have a file here that shows inputs, outputs, and applications and command lines. So nothing can go wrong, hopefully. So building Hermes is, of course, the first step. I'm not going to talk about that too much because all of that information is in the README. But you have several options. The easiest is just use the Docker image where Hermes is already installed. And then we also have the standard CMake build and a SPAC package. If you're not using Docker, SPAC is definitely the easiest way to install Hermes if you're familiar with that. But like I said, all those details can be found in the README on the GitHub page. So assuming we have Hermes installed, let's look at how we can configure it and deploy it. All of the demos that I'm showing today are assuming that we have a daemon program running, but Hermes can also be co-deployed with the application. But for simplicity here today, I'm using a daemon. And actually for adapters, if you're using multiple processes, so running an MPI application with Hermes, then in that case, you do need a daemon. Here's a small example of the basic Hermes daemon. We read a configuration file from this environment variable. We initialize Hermes as a daemon and we run it. That's all. This program is actually available already in the bin directory of your Hermes installation. So you don't have to write a daemon or anything. This is already there. If you install Hermes, it's in the bin directory. And this is a background program that when you initialize Hermes, it creates shared memory segments where it stores metadata information and buffering, buffers, RAM buffers, and initializes all the RPC and communication. And then it just sits there waiting for clients to attach to it. And the clients are spawned when you run your application. And there are a lot of options in this in that getting started guide that I showed. So for example, you can leave daemons alive and connect multiple applications, or you can run one application and have the application shut down the daemon. All that's covered in the getting started guide in the tutorial. For today, since I'm just doing one IOR run, I will spawn the daemon, run IOR, and just have IOR kill the daemon. So let's look at, before we look at intercepting an actual application, let's just look at what Hermes does by itself as the daemon program. I'm going to look at an example configuration where we just have one tier and one slab. When I say one tier, I mean one storage tier in the hierarchy. So for example, burst buffers. And then one slab, I'll explain that in a little bit. So this is a very basic configuration file. It's not a complete example, but it's the bare minimum. Showing the complete example is a little too much to put on this slide, but the place to go is the wiki, the configuration page on the wiki, and there you can read about the complete example and all the parameters you need. But the main thing I want to point out here is that I have two devices, excuse me, and I'm using devices synonymously with tier right now. So the devices correspond to burst buffer here and RAM here. Now, I only want one tier, so why do I have two devices? Well, currently you need to give Hermes a little bit of RAM for metadata. In the future, we would like to decouple that, but even if you're not using RAM for buffering, you still need a little bit for metadata. So I'm giving the burst buffer device 6 gigabytes, because this parameter is in megabytes, and I'm giving RAM 16 megabytes for metadata. Block size is the smallest unit of I/O, and since I know my application here is only doing 1 megabyte transfers, so I can just set the blocks of the smallest unit to 1 megabyte, and that's the most optimal for this application. I'm going to skip all this for a second because it's easier to explain with visualizations. Okay, so we pass the daemon this configuration file, we run it, and this is what we see. Our buffer pool metadata requires 246 kilobytes for metadata. That's just if you're interested. And then we see our two devices. Device 0 is RAM, device 1 is the burst buffer. Now, device 0 we see has 0 buffers, and that is because I said use 0% of that. Again, we hope to decouple that, but right now it's just for metadata. But device 1 has 6,144 buffers. And again, we know that each of those buffers are 1 megabyte because that's what we put in as the block size. And basically slabs are just multiples of that block size. And I'm not splitting it up any further, so I just need 1, 1, 1, and I just have one slab. They're all 1 megabyte blocks. And that's because I know the I/O is all in 1 megabyte chunks. Okay, and what does that look like? This is just I built a small visualizer program just to basically for debugging the Hermes buffer pool and metadata. So this is just opens up the shared memory segment and looks at what Hermes has in terms of buffers. So the red squares that you see on top are 6,144 buffers. And you can ignore the green for now. But the point I want to make is we have 6,144 buffers. They're all the same size. That's the simplest, most straightforward configuration, and there's only one tier. Also, if you wonder how much metadata you need, we try to tell you with the current metadata setup that you have in your configuration file. This example can support 64,000 blobs per node. Okay, so that's a straightforward example. Let's look at one that's a little more complicated deployment. Here I'm going to have 4 tiers or devices. For example, RAM, PMEM, NVMe, and burst buffer as an example. And now, obviously, your slowest and largest tier, burst buffer, you don't want really small blocks like you want in RAM, because then you're likely doing larger I/O amounts. So that's where this customization of all the blocks and slabs comes in. Here I've just given everything 4 kilobytes just to make it easier to explain, but understand that this is all completely customizable, and the more you know about your workload, the more you can tune these configuration parameters to align with your I/O. So let me show the output first before I try to talk about this stuff. We start Hermes with this configuration, and here now we see we have 4 devices, 1, 2, 3, 4, and under each device we now have 4 slabs, and these are just the indexes, slab 0, 1, 2, 3. We have many more small buffers, and as the slabs get bigger, which is to say as the multiples of our smallest unit size increase, we have fewer and fewer buffers. So we have 85 buffers of slab 3, which here we're saying that slab is 32 blocks, and a block is 4K. It's a little hard to explain this stuff, but visually it makes a lot more sense. Each slab is one of these groups of different colors. So the red blocks, the red squares are slab 0, and they are all 1 unit size. And then the next slab is the yellow one, and these are actually true to size. So the yellow slabs or the yellow buffers are 4 times larger than the red. The green ones are 4 times larger than the yellow, and the blue are 2 times larger than the green. Again, the main takeaway here is that this is completely configurable. You can have all of these, most of these red, some of them blue, most of them large, some of them small, and it's even dynamically configurable. If the system finds that you've used all of your small buffers, and you have a bunch of big ones unused, then it can actually dynamically split these big ones into smaller ones. That doesn't happen automatically yet, but we have that functionality, and in the future, we will try to detect that and cover that case. Let's see, the other point I want to make here, let's see. Also, yeah, so these are percentages. So this is the 4 slabs for RAM. You can tilt these percentages toward higher or towards lower, towards smaller or towards larger buffers. Here I've just split it evenly, 25% of the available capacity for each slab. All right. So now that we know what Hermes does when you give it a configuration file, let's actually run something. with it. IOR, like I said, it's a IO workload generator / benchmark. So I'm just going to have it do a bunch of IO for me. I'll start with the baseline, which is just using a parallel file system, and then I'll add Hermes, and I'll gradually add in more and more tiers. So start with burst buffer, then we'll give it some local NVMe, and then we'll give it some RAM, and see what kind of performance improvements we can get. Client info. I'm running this on 4 nodes, 46 gigabytes of RAM on each node, 40 gigabit Ethernet, and what I'm calling my parallel file system, or I also call it the final destination, because that's where the application thinks it's writing to. So that's the final destination. I have 8 nodes, and they are running OrangeFS backed by hard disks. All right, so again, this is the baseline. We're just running IOR. And we're writing to this PFS directory, which I've mounted as my OrangeFS parallel file system. I'm running 48 processes across 4 nodes, so 12 processes per node. And here I'll explain all my parameters for IOR. I'm doing write, so this is a write-only workload, no reading yet. My output file is on the parallel file system. My size per write is 1 megabyte. As we talked about above, since I know all I'm doing is 1 megabyte writes, I've tuned that in the configuration. Total IO per rank is 128 megabytes. So I'm doing 128 transfers of each of 1 megabyte. I'm using the F flag to create 1 file per process, because otherwise it will create all the ranks per node will write to shared files. We're doing file per process, which actually I should mention is the only parallel IO format that we support in the adapters currently, is file per process. And then I'm calling fsync on file close. That's just to mimic making sure your data is where it is so you don't lose anything. And then the last parameter, I'm doing it both ways. So I'm running it with the Y parameter, which means I'm calling fsync after each write. And the reason that I'm doing that is to simulate a workload in which your RAM is completely pressured. Because if your application is using all of your RAM, then the OS page cache won't have space for buffering, which results in kind of pure hardware speeds. So using that Y parameter and running this, I get 29 megabytes per second. And again, that's because no buffering has happened. That's the pure speed of the hardware over the network round trip. The data is on the disk after every write, which is not a realistic scenario. But again, I want to see what the actual hardware is capable of when there is no RAM available for buffering. And I'll talk about results at the very end where I can compare everything with a graph. So I'll just mention right now 29 megabytes for fsync after each write. And then I run it again without the flag. So there's plenty of RAM, so all the writes are being buffered. And then at the end, we call fsync, and the final transfer happens just one time. And doing it like that, our baseline for the parallel file system is 471 megabytes per second. Okay, so let's start adding Hermes. Let's add more storage hierarchy tiers to this. Let's start with just a burst buffer. And by burst buffer, I mean I have OrangeFS on 2 nodes, and they are backed by an SSD. And remember, the original parallel file system was a hard disk drive. So this is better hardware, but it's also fewer nodes. What changes about our configuration file? Well, we still have 2 devices, because remember, we need a RAM device always. And we're still doing 6 gigabytes capacity for the burst buffer. we are still doing 1 megabyte block sizes because that's our transfer size. And then all the slab information is the same. We just need one size. Don't worry about splitting it up into slabs. The only other change is I put my mount point in for the burst buffer, which I have the burst buffer mounted here. And that's it. And then of course the configuration file, you have to put in your server names and your ports and RPC information, things like that. But again, this is just the bare minimum for easier presentation. Now we have the configuration file. How do we actually run IOR with Hermes? 2 steps. One, we have to start a daemon. And again, if you're only running one MPI rank, you don't have to start a daemon. It can be co-located. And the native API as well, you don't have to start a daemon. It can be part of your application deployment. But here, since we're using MPI plus an adapter, we'll start a daemon. And the second step is to LD preload the Hermes adapter library. So let's take a look at how I'm running this. Let's focus here. One important thing to remember right now is that each node requires 1 Hermes daemon. So I'm starting 1 daemon on each node. In the future, we might be scaling that a little bit. Maybe 2 daemons work better, but right now we're limited to 1 daemon per node. So I just MPI run across my 4 nodes, 1 daemon per node. And all I have to do is pass through an environment variable, a path to a Hermes configuration file, and run the daemon in the background. Okay, give it a few seconds to start up. And now we run IOR. So the top and the bottom here are the same IOR commands that I ran above. I'm running my 48 processes across my 4 nodes, 12 ranks per node, tell it which hosts I want. And then on the bottom, my IOR command is exactly the same as it was on top. Output file, exactly the same, everything the same. The difference is I have some environment variables here. First, LD preload. I'm passing to LD preload the Hermes POSIX adapter library, which looks like this. When you install Hermes, you'll have this lib Hermes POSIX shared object. I pass that to LD preload. I pass my configuration through an environment variable again. Same configuration that I give to the daemon. And then here, since we know it's write only, there's a few optimizations the library can do if it knows it doesn't have to keep things around to be read. So I add that. And then I change the adapter mode. Now, the default mode when you're running a Hermes adapter is to leave the file in the final destination, the place where the original application expected the file to go on the parallel file system. When the application finishes, that file should be there, right? That's the default behavior. But in this case, I just want to show the hardware performance and how Hermes can intercept the I/O and put it to the new hardware. So I'm doing scratch mode. So at the end of this run, nothing will be on the parallel file system. Hermes will shut down and just forget all the data because it was just scratch data on local media, and we don't need it anymore. So adding 4 environment variables, that's all you have to do. And again, I'll talk about results at the end where I can show a graph and compare everything. But using burst buffers, we get 335 megabytes per second. So now let's add some NVMe. Configuration is very similar, except now we have 3 devices. So I just, instead of 6 gigabytes for burst buffer, I split it off 4 for burst buffer, 2 for NVMe, and set the block size. And again, I'm not doing any slabbing, so everything is just 1 unit. I add my mount point for the NVMe, which is a local drive to each node, and run it exactly the same as before. Just make sure you pass the different configuration file through that environment variable. And now we're up to 514 megabytes per second. Burst buffer was 333. Okay, so now let's assume we have some RAM, or that the application is willing to relinquish a little bit of RAM to Hermes. Only a couple changes here are, we still have 3 devices. The only difference is now we boost this RAM up a little bit, 512 megabytes. And whereas before we were giving 0% of that to buffering, here we'll give 100% of that to buffering. It will still take a little bit of that for metadata. So when you put 512, you don't exactly have 512 megabytes for buffering because metadata takes some, but close. And we run it the same as we ran it before, and we get 829 megabytes per second. So let's look at all of the results together. On the right here, we have, without Hermes, our 2 parallel file system runs. First, where we f-sync after every write to replicate RAM pressure. And second, parallel file system with normal OS page cache buffering. And then on the left here, these 3 columns are when we add Hermes. So burst buffer, add a burst buffer, and we have 335 megabytes per second. Now that's slower than what we get with the PFS. And what that tells us is the better hardware of the burst buffer, which is SSD over instead of HDD, the better hardware, the speed up we get from that hardware isn't enough to overcome, one, the fact that we have a lot more parallel file system nodes than we have burst buffer nodes, and 2, just Hermes overhead in general. Now, as less buffering space and RAM becomes available for the OS page cache, then I would expect to see this number outperform the PFS plus RAM number. Because again, if you're looking at pure hardware without buffering, remember parallel file system is 29 megabytes. Burst buffer that I measured here was 100. So a lot of the work going on this year, we haven't done any optimization yet. So this is just, we're getting feature complete, and then we will, start optimization. So without any OS page cache interference or help, the goal of our optimization will be to push the Hermes performance as close to that hardware maximum as we can. So burst buffer right now, not quite as fast as PFS plus RAM, but we add in some local NVMe space and boom, we get faster than using parallel file system. And then add some RAM and we get 1.75x speed up over the parallel file system run. And the really cool thing to emphasize here is, like, to make this jump from this column over to this column, all we had to do was change this number, and that's it. That's really cool to me, and also this number, I guess. So these 2 numbers, and changing those 2 numbers automatically diverts that I/O from one storage hierarchy to another, and you can see the results of it right there. Now, I know, like I said, this I'm doing this in scratch mode, so we're not seeing our data end up at the final destination. So it's not quite apples to apples, but we actually have already done workloads like that where the key to making those apples to apples comparisons perform is overlapping the flushing to the parallel file system with compute. So in a sense, it's the same thing, but as soon as your data ends up in the storage hierarchy, Hermes can queue a flushing task so that your data, since it knows it's write only, that data will just start migrating down to the final destination in the background and hide that I/O with overlapping compute. But for this demo, it's just a scratch demo. Let's see. Yeah, and again, this is no optimization yet. I expect to get a lot better than this as the year goes on. That is the demo. And again, I encourage everyone for feedback if they're try it out with your application, and if it doesn't work, please open an issue, and I'll send it back to Anthony. Thank you.
Well, thank you very much, Chris, for the demos and the presentation. Pretty cool results, right? So I guess the goal here today was to demonstrate that the existence of multiple tiers of storage can be used and leveraged to boost applications' effective or perceived bandwidth, right? You saw in the demo, like you started with just 2 burst buffer nodes and you added a little bit of NVMe and boom, you had like 40, 50% improvement in performance. And then you added a little bit of RAM into this hierarchy, and then again, you get more and more performance. Is this gonna be ever apples to apples comparison with a parallel file system deployment? Well, no, because the environment is different, right? So in one hand, you have a single tier environment. On the other hand, you have multiple tiers. And the effect, another messaging here is Hermes is a distributed IO buffering, right? So another thing we're competing against is the page cache. Like effectively, already all IO happens in buffers. Like the operating system is buffering already a lot of the requests and then push them down to the hard drives. So we're competing in a sense with that. That's why Chris just demonstrated that effect, that page casting is a luxury. And people don't always understand that. Like it's not always the case that your IO can benefit from that, because either you have limited RAM environments or your RAM is already utilized by the application structure. So really IO happens against your storage system, whatever that storage system is. So Hermes is a very easy way to kind of optimize that. So let me see if I can share my screen again. Can you see my screen?
Yep.
Okay, cool. So with that, I want to go over a few of the questions we have received, during different outreach activities in conferences and workshops and tutorials and webinars, and what other people have asked us, and maybe some of the audience here can relate to. So how does Hermes integrate into an HPC environment? Like how do you use it, right? As of now, applications can link to Hermes, dynamic linking, or recompile it with Hermes if you want. And we will have some efforts to integrate Hermes with a system scheduler to provision buffering resources. What does that even mean? At this stage, the user goes out, gets some resources, goes to the scheduler, says, hey, I want to run my job. It gets like 100 compute nodes. If those compute nodes have NVMe drives, these are accessible to Hermes. And then we go and run Hermes on top of those machines, and we manage these NVMe devices for the user. But then in the future, you may want to have like more dynamic provisioning of resources and let Hermes manage buffering resources in a way. As we said, Hermes can also be run as a service. You can spawn the Hermes daemons before your application starts. That's particularly good for workflows where you have a producer consumer logic. You have a simulation producing data and you want to kind of analyze or visualize this data. You don't want to send everything to the parallel file system necessarily, right? Because you don't know if you're going to keep this data. So in these scenarios, buffering makes total sense. That you just push the data to Hermes, into those Hermes daemons, the simulation job exits, and then you start an analytics job or a visualization job. Your buffer data are still there. And this can go on and on and on workflows and complex workflows. And the user decides when to kill the data, to kill the Hermes. In these situations, Hermes can either flush data to the parallel file system or just delete data. As Chris said, it depends on, is this a scratch mode or is this like a persistent mode? And then some of the HPC environments we've seen to start supporting containers, and there's like Singularity and Docker, and a lot of scientists are requesting this kind of thing. So we already have Docker images for Hermes, and it should be easy to deploy Hermes in environments like that. What are some of the Hermes build dependencies? I guess they're just listed there. I don't know if Chris has a comment about it, but all of this is pretty well documented on the README. We're trying to reduce the dependencies as much as possible, but we need a high performance RPC framework, and we want to build upon the success of other projects, like Thallium is something like that. We're using the Google logging library to do error messaging, and we have some optimizations into the data placement engine and how we distribute data. We use linear solvers from the OR tools, and so on and so forth. Does running Hermes require any elevated privileges? The answer is simple no. Does not require administrative privileges and is designed to run in user space as an application extension. And this is, again, something that we heard from the community. A lot of the times you don't have access to this kind of things. You don't have elevated privileges. How can you use some of these technologies, right? So we wanted to make sure that you can use it easily. How to get started with Hermes, and do I need to make changes to my application? Well, the answer is yes and no. There are no code changes with ULD preload. If you're doing already some file IO, and our adapters, POSIX, standard, MPI will intercept that IO and will redirect this traffic to Hermes. There are situations where maybe minimal code changes are required, like setting an environmental variable to say, hey, I want you to use this virtual file driver in HDF5. And we have developed a Hermes virtual file driver. And of course, the most power, the most benefit comes from using the native API, mainly for new applications, and you wanna give Hermes a try, like just test drive it in a way. And this is where most of the power is, because we adapt our own buffering data model based on blobs and buckets and some other interesting constructs, which are all well documented in the wiki and in the documentation of the project. How scalable is Hermes? Well, it should be as scalable as what our RPC components we're using. So on paper, it should be very scalable. Our development process at this point consists of 64 nodes. And of course, this is a small scale, but it's the development test that we have, and it's a hierarchical system built for this project that has, RAMs and NVMEs and persistent memory, and all kinds of different storage devices and storage hierarchies. Scalability testing is an important activity over our next year, and we invite, people like, give us your application, or let us help you optimize your IO and try to scale it and try to grow with you. Which MPI implementations are supported? For the native Hermes API, we support OpenMPI, MPitch, Intel MPI. At the MPI IO layer, the adapter we have, it currently supports MPitch only, but it happens to use a few of certain MPI status in 3 places, so it won't compile really with OpenMPI. We will work to remove these things if necessary. Like if someone really has those cases, we will happy to assist and remove dependencies like that. What data placement strategies are available in Hermes? Can I bring my own? Those are great questions. The data placement engine itself and in the hierarchical space is configurable and extensible. Currently, we have 3 strategies or policies, strategies in this case. Random, its blob is distributed randomly between buffering targets, and that random policy just favors load balancing. You want to like spread everything out uniformly. Round robin kind of mimics parallel file system distributions. Its blob goes to the next available target in a round robin fashion. And then we have some constraint-based placements, linear optimization, linear solvers, as I mentioned earlier. We take its blob, we decompose it in different subset, and we distribute all of that in the best available buffering targets based on different constraints. Like maybe you want to say as a user, hey, I want you to use all the available buffering targets that have more than this capacity, or that they perform more than this threshold. Those are all kind of configurable. And we will provide an interface for user-defined placements. We have some initial work with an XML. You define a few things on your XML file. We parse that thing and we push this information into the data placement engine. Every time it sees a file open and that specific file is supposedly buffered in a certain way, we will respect the wishes of the user. How do I prevent specific paths from being intercepted by an adapter? Typical interception problems, right? You want to exclude those paths from the Hermes adapter, and we will provide an environmental variable to facilitate that. Are there examples of how to use Hermes native API? Yes, we have a bunch of different examples. We will make available the slides and the recording of this webinar after the webinar, so you'll have all the links. But again, everything resides on GitHub. All of the things are there. I would say you could start with the end-to-end test. We're running out of time, but I'm running almost over here. How much RAM should I set aside for Hermes buffering? It should be configurable by the user. Whatever you feel is necessary. If you're doing data-intensive science, give a little bit more RAM. It's a data-intensive workload. It will be optimized more and more. So it depends on the system you're running and the workload you're running. What is the trade-off between applications on Hermes? Obviously, more RAM can lead to higher performance. Less RAM, it's kind of like you're skipping your entirety. We can operate without RAM at all, obviously. RAM is optional. The footprint on metadata, Chris also touched something on his demos. We do use some RAM, of course, for metadata. A lot of these things stay in RAM, and they get persisted into different persisted devices if necessary. Is there any interference between Hermes and VO Spacecast? There is no interference. And again, as I said a little bit earlier, it's a long story between competing with what the OS is doing versus what the buffering library specifically is doing. Is prefetching currently supported? Almost there. We're going to release it in a subsequent beta release shortly. And the configuration stuff, Chris talked about it. So with that, as I said, we want to thank you all for attending. Please feel free to contact us if you have any questions or any requests. Remember, you can find information on GitHub, and we do have another session in 20 minutes from now that it provides a more informal roundtable conversation with you guys and the developers and the Hermes team. Feel free to join us. I'll put this link to the chat if you guys want to join. With that, I would like to conclude and thank you all attending today. As I mentioned, the recording will be available and it will be emailed to you after this session.